Hello, we will be going through the solution to number 3. I didn't get too carried away with visuals, so if it doesn't make sense as I'm describing it, just send me a message on Google Chat and I can walk through it in more detail with you. But this is a great example of a lab-based question. These are tough because they're not straightforward as far as this is exactly only one method of doing it, and you'll see in the rubric they have several different alternate expressions that would earn you credit. So if you got questions, follow up on Google Chat or in Google Classroom. All right, this lab-based problem is, it's pretty straightforward, but it has some tricks to it that make it a little bit more complicated. And so as we walk through this, I want to explain why we can and can't do a few things. At first glance, there's a couple equations that really stand out for part A to answer that, because in your toolkit you'll have a really straightforward equation that says the force of a spring equals K times displacement. And if that were, all we needed, all I'd have to do is just record the force of the spring and the displacement of the spring. I could use a force sensor, a spring scale to get force, and then I could use a meter stick to get displacement, and I could just solve for K. And although that works, we got to be careful. Down here it says state a basic physics principle or law that the students could use in designing an experiment. When they refer to a law or a physics principle, they're looking for either conservation of momentum, conservation of energy, or possibly Newton's laws. And so I think what they're going to want us to do is go at it from a different perspective and get it through the energy equation and do conservation of energy. So the energy of a spring is equal to 1/2 K times displacement squared. It's a lot of the same stuff that we need as far as displacement, but we're going to have to get creative with how we solve for the energy. So I think that's what their goal is on this, is because they said solve it with using a physics principle or law. They're going to want it to be set up using conservation of energy equation. So using that principle, determine expression for the spring constant in terms of quantities that can be obtained from measurements made with equipment usually found in school. So in this case, we have to talk through a little bit of the setup, but pretty much if you know that you're storing spring energy here and it launches, let's say, as kinetic energy, you could set these two formulas equal to each other. That's one way of doing it. So we would just need to set up an experiment to get values of velocity and get the mass of it. So just put the ball in a balance. If I did it another way, if I did it vertically, just turned the thing on its side and launched it up in the air, I could record the height. And if I record the height, then I can set it equal to gravitational energy. So spring energy down here set equal to gravitational energy. But the principle is the same. It's the conservation of mechanical energy is what's going to help us solve for this this device. So let's set it up. I think the horizontal launch makes more sense to me. So setting spring energy equal to kinetic energy, that would be 1/2 kx squared equals 1/2 mv squared. And so from that, you would get KL by itself. Divide by x squared on each side. And so finally, I'd have that K would equal mv squared over x squared. So as far as these variables go, quantities to be measured, I'm going to have to get the mass, I'm going to have to get the speed, I'm going to have to get the displacement of the spring. Most of those are pretty straightforward. Anytime you get mass, you could say put it on a balance, but a triple beam balance is kind of old school where you don't have to have a digital mass or a digital scale, but you could say a scale. So we need mass to be measured, and that symbol is M, and the equipment for that is a balance of some type, a triple beam or just a digital balance, you could say. The second variable is velocity, and you could do several things. You could use a motion sensor That's pretty easy. Photo gates, you could walk them through how to set up photo gates to do that. You could just do a meter stick and stopwatch. You don't have to write all of these. I would just stick to one. Motion sensor is the easiest. Just a motion sensor that could spit out the velocity would be ideal. But these are things that they expect that a physics room would have. Then the last variable I need is displacement. And so let's say like the compression of the spring. And that's going to be delta x. And we just need a meter stick for that. So using this energy method, that's what we need. I can show you that if you use the force equation later on, you would have got some points if you used this one right here, force equals kx. If you went through most of this question, you probably get half credit. But to get full credit, it's going to rely on that you actually launch that ball and set energy conservation as a method of getting to the answer. So we'll move on to part B. All right, for the second part of part B, they want you to describe the experimental procedure so that someone could replicate it. So just be sure you don't skip any steps and you kind of walk through what you would need to do. To test the hypothesis, you're going to have to test at all three clicks, like A, B, and C. So make sure you include that you're going to repeat the trial at all three locations to compare. And you're going to measure out the mass of the ball. You're going to launch it. You're going to record how far you compressed it back with the meter stick. Then you're going to launch it, and then using a motion detector, you could look at how fast it's going to get the kinetic energy as soon as it leaves the setup and set those two equations equal to each other, solving for K. Next part, it says determine what could be analyzed to confirm or disconfirm the hypothesis that the spring constant. So pretty much what you're saying is that if you compare the K value at all three of those locations, and if it's the same, that would confirm that it is constant. If you got different values of K at all three locations, then that would say that it's not constant. I'm going to switch over to the rubric so you can see how they would have awarded points for this section. It's way down here. Sorry, let me pull this up. Zoom in. Sorry, don't want to make you sick, but this is just the fastest way I could do this. So let's just kind of walk through how they gave points so far. In part B, you got 1 point for just listing appropriate equipment and those things that would measure the quantities. So here they say that this point can be earned if the sphere is not launched. So that's what I was talking about with that force equals kx equation. You could get points even without saying that you had to launch it. Same for this one, for describing measurements of quantities sufficient to determine the spring constant, so making sure you listed all those variables that you need. For a plausible procedure that can be done in a typical physics lab that involves launching the sphere. So this is where you actually need to launch it to get these other points. And then saying from launching the sphere at these at least two initial positions. I would just say all three because you have them available. And then 1 point for attempting to reduce uncertainty. So multiple trials and getting an average, something like that, so that you indicate an experimental procedure that would cut down the error with just one data point. Let's say you just fired it once and you might have got a bad reading on the motion detector. That's not a consistent way of doing that. So take a few trials on each and average them. So here's an example. They got the mass. Okay, they labeled things a little bit more exact than I did, but you can see that they're looking at a similar setup of energy conservation. And firing it horizontally, the mass is launched, motion detectors record the launch speed, and it's repeated 3 times at position A. That way you can average that out, and then you would repeat that same process at positions B and C. So if you're just going to repeat one thing at another location, you don't have to write it all out again, just say repeat that same process at those other locations. A second procedure is they're like you fired a horizontal distance and record that like a projectile launch, so you could work backwards and solve it like a projectile of a sphere, and that would work as a separate method to determine how far it goes. So I'm going to minimize this again. Okay, and bring us back into here. So then, part D, another student uses the launcher. Yikes. Sorry. Doesn't want to. There we go. Another student uses the launcher to consecutively launch several spheres that have the same diameter, but different masses, one after another. So each sphere is launched from position A. Consider each sphere's launch and sketch a graph of launch speed as a function of sphere mass. Well, just using our formula over here, we can kind of get an indication of, whether or not mass is going to have an influence. You have mass here and, so mass here and launch speed here. And the fact that they're side by side in the equation, changing one may have an impact on another. So if the displacements are all held constant, and if we have the same spring constant, then they really do have to operate off each other. If this goes up, this is going to have to go down, but it's kind of tricky in the way that it's set up. So it's inverse square related, the way that these are set up. And so as your mass increases, your launch speed is going to go down by a factor of that squared. And so it's going to look like that because mass is proportional to 1 over v squared. Being side by side like that, as that one goes up, the other's going to go down. There's your inverse part, but the fact that it's squared has this effect. So that is how you graph launch speed versus sphere mass. So now looking at the rubric for part C, just kind of walking through that. Here's an example. For each pin position, take the average. This would be actually like, not for the same setup that we did. Let me go to, yeah, here we go. So experiment analysis 1 is closest to what we did. So for each pin position, take an average of those values, then calculate the spring constant using this equation. And I already kind of showed that at the beginning. But then K would equal mass times velocity squared over displacement squared. Then compare the K values. If the value agrees within experimental uncertainty, the hypothesis is confirmed. You don't even have to say how you get experimental uncertainty. You just have to say that you would try that over and over, and hopefully they would be the same. That would confirm the hypothesis. In part D, this is what we were just talking about, that because mass and velocity squared are inverse square related, you get 1 point for just drawing a curve in which the speed always decreases with increasing sphere mass, and for a curve that is entirely concave up and has the launch speed always decreasing. You don't even have to really know that it's inverse squared. So this math of like mass is proportional to 1 over v squared, they don't even need that much of it, as long as you just show this concept that it's not straight linear, it's curved. And that is all you need to do for that question.